right, ladies and gentlemen, Youngsoo is our guest today, our guest speaker. He will be talking about interpretable and structure-preserving data-driven methods for physical simulations. Directly handing over to you, Youngsoo. The stage is yours.
All right, thank you so much for the invitation, Joseph. It is a great opportunity for me. Today, I would like to talk about interpretable and structure-preserving data-driven methods for physical simulations. These are the collection of methods developed at Lawrence Livermore National Lab. And I will try to combine all of them in a storyline with a consistent theme that is a interpretability. All right, before I dive into the main presentation, I would like to recognize wonderful reduced total model teams whom I was fortunate enough to work with. Plus, without these collaborators, I wouldn't be able to present what I am presenting today. So big thanks to all of them. All right, the physical simulations play an important role in modern science. I do not think anyone here will have an objection to what I have just claimed. If the physical simulations were not important, we, for example, Lawrence Livermore National Lab folks, wouldn't have gotten the worldly known high-performance computing facilities on site. If the physical simulations were not important, the concept of digital twins would not have emerged. For example, these days, various physical simulations have been developed to better understand the process of 3D printing. The simulation for 3D direct energy deposition is one example, as shown here. And shockwave hydro simulations are important for multiple applications, such as automobile, aircraft engineering, geological science, nuclear physics, and so on. And electrostatic ion scale turbulence simulation on tokamak fusion device, which is shown here, which is simulated by the production code COSENT, is important as well for plasma physics point of view. And multi-physics simulation, such as 3D shape charts simulation, as shown here, is important for national security applications. And pore collapse simulations is essential to understand the high explosive physics. There are many more important physical simulations, but one potential and major problem with these examples is their computational cost. Some of them are actually manageable, such as 3D direct energy deposition here, and 2D shockwave simulation, which takes an hour with multiple cores, are not that bad, right? However, more involved simulations, such as tokamak simulation, 3D shaped chart simulations, and pore collapse simulations are just too expensive computationally. This is unfortunate for many decision-making applications, such as design optimization, uncertainty quantification, and inverse problems. Because there, we need to run these forward physical simulations many times as we explore parameter space. Therefore, we need a fast simulation capability. All right, what if you can do a fancy, complex multi-physics simulations within a minute with your personal laptop or even with your smartphone? That sounds hard or almost impossible for now, but if it is possible, we can do many cool stuff. For example, you can design things faster that will reduce the cost of the overall manufacturing or analyzing or preparing experimental settings or anything you want to do with physical simulations, right? That would be so awesome. Indeed, today, I'm going to talk about how we can accomplish that using data. By the way, let's ponder a little bit about data. Data is a cool stuff. If you think about it, it was the observational data that allowed our view change from geocentric to heliocentric world. Collected observational or experimental data were the ones that enable numerous scientific discovery, such as Newton's law of motions, law of thermodynamics, electromagnetics, and so on. Even now, data plays an important role, especially when machine learning and artificial intelligence are so prevalent. In modern science, the data can do many things, but I will focus on one thing, that is accurately accelerating physical simulations. Because simulations being able to accelerate, because this accelerating the physical simulation is so important, we can do a lot of things with it. All right, how can we accelerate the existing physical simulations with data? Just to illustrate it, let's say we would like to build a fast surrogate model for heterogeneous porous media problems. More specifically, let's say we would like to find out pressure field for a given heterogeneous permeability field. Well, you can first generate simulation data by running many porous media simulations with different heterogeneous permeability inputs that will give you many pairs of input and output data. Now you can relate these input and output data by, for example, training a neural network. Here we have trained a conditional generative adversarial neural network for this particular problem. Once a neural network is trained, it is easy to predict a new pressure field by inserting a new heterogeneous permeability input to this neural network. The evaluation of the neural network is fast, and if the quality of the neural network is good, then it will give accurate prediction. For example, the conditional adversarial neural network we trained for porous media problem, we get accurate solutions as demonstrated in these pictures. Full order model and the surrogate model solutions are basically indistinguishable, as you can see from these pictures. By the way, this is a black box approach because we blindly relate input and output data with some neural network structure, which we do not have much control on and which we do not understand deeply. So once the neural network is trained with some given data, it is what it is. In that sense, it lacks interpretability and explainability simply because this neural network structure is not familiar enough to us yet. The black box approach is so popular because you only need data. You do not need to know how you solve physics problems numerically. In that sense, it is non-intrusive. You do not need to go inside of the physics code and debug things. As long as the simulation data is good, then you are good to go. Therefore, it requires less development time than other data-driven approaches, which are more involved. Plus, there are great tools out there ready to use, such as PyTorch, TensorFlow, and many others, as you may probably know. They come with automatic differentiation tools, so you can manipulate the neural network operators very easily to fit them to some differential forms. However, the black box approach does come with some disadvantage, though. Because it relies heavily on data, it needs big data, which is not cheap to generate if the data are coming from computationally expensive simulations. Because it relies heavily on data, the black box model cannot accurately predict the solutions for the regions where you have not seen any data. That is, it is not robust for extrapolations. Plus, the model itself is not easily interpretable, as I mentioned in previous slides. What if when it fails, we do not quite understand why it fails. When it does the job, we do not quite understand why it does the job. Additionally, because the black box approach do not incorporate any physics informations, certain physical properties such as symmetry, positivity, conservation, etc., are not guaranteed to be preserved, which really concerns physicists. Lastly, but not the least importantly, the training of the neural network tends to be very computationally expensive. This point is somewhat arguable because other black box approaches such as Gaussian process or Kriging or the random forest are easy to train. I'm specifically addressing this issue with the neural net. Its training is computationally expensive because it involves complex nonlinear optimization solves. Plus, its convergence behavior can be very problematic. Well, then, how can we get an interpretability? We have to somehow relate this data-driven model with what we are already familiar with, the things we have studied for a long time. For example, ordinary differential equations or partial differential equations. To illustrate that, let me consider a simple red-IO advection problem, which is described by a well-known partial differential equations. You solve it using some numerical schemes such as finite element or finite difference methods. Then generate simulation data. This data is high dimensional, so it would be hard to fit them directly into some model. Plus, remember that our goal is to build a fast model. To build the fast surrogate model, we better deal with reduced space dimension. Therefore, we compress the data, which, for example, leads to the latent space dynamics data with dimension of only 3. There are 2 types of compression in general. First one is linear compression, such as proper orthogonal decomposition. Tensor decomposition falls into this category. And the other one is the nonlinear compression, such as autoencoder, generative adversarial network, and so on, falls into the nonlinear compression category. Now, going back to the latent space dynamics, this low-dimensional subspace, the data is a lot easier and more manageable to fit into a model. Which model would you use? Note that it is time-dependent data. Remember, Isaac Newton wanted to describe orbital motion, which is also time-dependent data with a model. What did he come up with in the process? Calculus, or the differential equations. Yes, we can fit the latent space data into differential equations. For example, linear ordinary differential equations or quadratic differential equations, and so on. By the way, if we choose to use linear differential equation, then we are more or less using the famous method, that is dynamic mode decomposition, so-called DMD. The DMD fits latent space dynamics into linear ODE model. We know a lot more about linear ODE than neural network. So this approach is, although purely data-driven, it is interpretable. For example, if we happen to know this A hat matrix here, which is small, explicitly, we can perform eigenvalue decomposition and write an analytical solution for the linear ODE in terms of eigenvectors and eigenvalues. For example, if the real part of the eigenvalue is greater than 1, then the solution will explode. Therefore, we should make sure that the eigenvalue does not exceed 1 if we know that the true solution does not explode. Here, eigenvalue serves as an indicator, which tells us why the model fails if it fails. By the way, DMD requires only data, so it is not an intrusive method, which requires less development time than other intrusive methods. So we were able to apply this DMD to many different physics problems pretty quickly. Let me introduce some of them now. The first DMD example is on the heat conduction problem, the toy problem. The DMD can be parameterized easily by interpolating DMD operators. To demonstrate the parametric capability, we set 3 parameters, that is the radius of the circular, the initial conditions, and the X and Y coordinates of this radius, the center of the circle. By following the same procedure of generating the training data and building DMD, it has been tested for several points which were not used in the training sets. As you can see, the DMD was able to predict the solutions quite accurately, less than the relative error being 1%, relative error being less than 1%, which is pretty good. This parametric DMD can be used to accelerate multi-query applications. For example, let's say we would like to find out radius and X and Y coordinates of the initial condition that produce a target temperature field at the late time step. This can be formulated by minimization problem, where the last time step DMD temperature needs to be as close to the target temperature T target as possible. To illustrate this, let's say we would like to achieve this particular target temperature field. We solve the minimization problem with differential evolution algorithm, which iteratively finds an optimal solutions. For example, it generates these intermediate latent time steps, DMD temperature fields, and finally declares that it finds an optimal solution, which is generated by radius and x and y coordinates of the initial condition that are close to 0.2. Indeed, we have originally generated this target temperature with initial condition parameter of 0.2, which gives us 2.3% relative difference, which is pretty good. All right, another engineering problem that we have applied the DMD to was 3D printing process. Not long ago, 3D printing has revolutionized the manufacturing sector. With 3D printing, you can make almost any object with any complex shape. In order to make 3D printing process as precise as possible, it is important to be able to accurately simulate the 3D printing process. As the 3D printing simulation model becomes complex, though, the computational cost becomes too much. For example, the full auto model of this simple laser heating the test bed, the process simulation takes a couple of days, while the DMD simulation takes a couple of minutes, achieving a great speed. Plus, a great accuracy was achieved, that is a relative error around 2%. Another physics problem that we have applied DMD to was pore collapse simulations. When a shock wave hits the pore in the middle, it introduces interesting hot spot, as you can see from this movie. It just hits the pore, and then this temperature field is showing very interesting temperature fields. And we trained a local DMD with the full auto model simulation data at 13 gigapascal pressure shock wave, then predict the solution for other pressure shock wave from 11 gigapascal to 15 gigapascal. For example, the prediction at 15 gigapascal DMD solution looks like this. Both full auto model and DMD solutions are almost identical in eyeball norm. Quantitatively, its relative error was around 8%. This demonstrates the extrapolation capability of the DMD. And by the way, this extrapolation capability can be improved by taking some modified the approach. We call it the distance windowing approach instead of the time windowing approach, the approach we originally took. The distance windowing approach takes advantage of the physics indicator, such as the traveling distance of the shock compared to the time windowing approach, which simply chop up the temporal the domain. For the computational time, while the full auto model pore collapse simulation takes several hours, the DMD training takes only 1 minute, and the prediction time takes only 8.3 seconds, which give a tremendous speed up. Another nice thing about DMD is that the training cost is not comparable to the one for neural network, for example. We have applied both neural network black box approach and the DMD to shock-induced flyer plate dynamic problem. We are generating full auto model data took 52 minutes. Neural network training time took 4 hours, while the training of the DMD took only 4 minutes. The interesting fact is that this neural network used downscaled data. That is, the original full auto model data was actually 2048 times 1349 pixels, but the downscaled data for neural network was 128 by 128 pixels. Despite the reduced size of the data, neural network took 4 hours for training. On the other hand, the DMD did not need to downscale the data. At the same time, with the original data, DMD was able to train it within 5 minutes. And also look at the accuracy. The DMD gave a better accuracy than the neural network. I would say that this shows a power of the interpretable, the DMD approach. We have also applied the DMD to Kelvin-Helmholtz instability problem, where we achieved about 900 speedups with a relative error of 1%, which again is a wonderful result. And finally, DMD has been successfully applied to other interesting physics, such as 1D, 1B Vlasov plasma physics problem for two-stream instability, 2D Euler equation for Riemann problem, and 2D Navier-Stokes equation for lead-driven cavity problem. For all of these problems, DMD was able to generate not only good accuracy solutions, but also considerable speedups, such as 33.4, 79.3, and 1848 considerable speedup. All right, enough for DMD stuff. Now I would like to ask the following questions. Are there data-driven methods other than DMD which are interpretable? The answer is yes. Let's go back to the radial advection problem for DMD after the compression of the high-dimensional simulation data to a low-dimensional latent space. We fit the reduced the dimensional data to linear ODE. However, it may be that the linear ODE is not a good fit or a good choice. Actually, one can imagine fitting the latent space dynamics data to higher order ADE or ODE, or even to an ODE with trigonometric or exponential right-hand side. This is exactly what LASTI does, which stands for Latent Space Dynamics Identification Method. SINDI types of sparse regression technique can be used to fit the latent space data to user-defined ODE, but we do not enforce sparsity here when we do the regression, because our main motivation is not to come up with an ODE with sparse terms, but to best fit the data to given ODEs by minimizing the error. And this approach is again interpretable because our latent space dynamics model has a familiar ODE forms. Now we want to make this LASTI framework robustly accurate when the parameter changes. There are many different ways of making the framework parametric. First of all, we only want to deal with latent space model, not the full order model, which implies that parameterization must be done within the latent space. Let me show you one way of doing it. Here is a parameter space D for each training parameter point. For example, parameter point mu1. We can build a tailored ODE that best describes the latent space dynamics at that point. Note that coefficient matrix A sub hat depends explicitly on mu sub 1. You can do the same thing for mu sub 2, mu sub 3, and mu sub 4, and mu sub 5, and so on. Then you can interpolate the linear coefficients of the ODE for a testing point mu star. Note that the coefficient matrix A depends explicitly on the testing parameter mu star, as well as all the training points. As you can easily imagine, you can apply similar interpolation for other testing points. We have applied this LASTI framework to the radial advection problem by parameterizing the initial condition with two frequency values, W1 and W2, shown here, W1 and W2. For this problem, we took uniformly sampled training points as shown in this graph, 5 by 5, the pixel, which gives 25 the training points in total. For each training point, we generated the high dimensional simulation data. Then we compress them to latent space with a dimension of only 3 using autoencoder. Then the coefficient of the ODEs that fits the latent space dynamic data were interpolated. This heat map shows the relative error on a given parameter space. The matrix, the maximum relative error was 5.4%, which occurs here. That and the last framework was able to give us a speed up of 200 when compared to the full order model simulation. Decent results, right? But we were not happy about the fact that the high relative error concentrated on the particular region, which is the right side here. So if you think about it, this caused by certain sampling method we adopted, which was the uniform sampling. As you can see, these sampling points were uniformly distributed. However, with the better sampling, we can even decrease the accuracy or improve the accuracy of the model even further by using the same number of data. The physics-informed the sampling is what I'm going to introduce right now. We have actually developed such a non-uniform sampling, the physics-informed sampling procedure, and we applied it to the same radial advection problems. This is the comparison between the physics-informed greedy sampling and the uniform sampling. As you can see, the same number of the testing data and the training data were used, which was the 25. However, the non-uniform sampling guided by the physics, the informations, were able to achieve the maximum relative error of 2.5, 2%, around 2% here, while the uniform sampling, it was 5 point something relative error. So how do we achieve this physics informed the adaptive sampling? We followed an active the learning paradigm where you adaptively append the training data while the autoencoder is being trained. For example, you start with 4 corners in the parameter space, which were marked by 4 empty squares here, where we run simulation data and generate the data and then check if the number of training points reach the maximum allowed. Let's say we are willing to spend 10 training points in total. Since we only have 4, we are going to move on to the next step, which is the training of the autoencoder and dynamical identification process. Because the autoencoder and the dynamics identification steps must communicate with this adaptive sampling procedure, we combine the latent dynamics identification step into the autoencoder training by adding the latent space dynamics regression terms as loss function terms. So there are 3 terms in total in the loss function. The first one is a typical reconstruction loss for autoencoder, which takes the difference between the original high-dimensional simulation data with reconstructed one through encoder and decoder. The second and third loss terms are related to the latent space dynamics regression terms. We go through several epochs to pass, say 2000 epochs to minimize these 3 loss terms simultaneously with the current training data, which we had 4 now. Then we go back to the sampling where we apply random validation points. At each validation point, we compute the physics-informed error indicator. We find out where the maximum physics error indicator occurs with the current autoencoder and the dynamics identification model. In this picture, this red point here is giving us the maximum error. So we take it as a training data and generate simulation data there and add it to autoencoder, the training. And we repeat this process until the desirable accuracy or the maximum number of training points are reached. If you want to know more details about this physics-informed greedy sampling procedure, you can check out this paper here, or you can watch this short YouTube tutorial video. It's less than 10 minutes, so I'm sure you will enjoy it. All right, enough interpretable, the data-driven method for now. How about the physics-constrained data-driven approach? If you can somehow incorporate the physics in your data-driven method, it will be for sure interpretable. And that would be the most desirable thing because it will be easier now to preserve some underlying structures, such as conservation, symmetry, and positivity. To discuss that, let's go back to the page where I described the process of compressing high-dimensional data. Again, after the compression, you get the latent space dynamics data with a reduced dimension. The interpretable data-driven approach was to fit this data into a user-defined ODE. Well, instead, what if you derive a system of ODEs that describe the latent space dynamics data from the original governing equations? Is it even possible? The answer is yes. One way of building such a system of ODEs for latent space dynamics is given by traditional projection-based reduced order models. To explain it, let's start with the governing equations represented by the ordinary differential equations. You can consider it as a semi-discretized version of the partial differential equations that describe your underlying physics. Here, W is a state variable, F is a nonlinear function, and T is the time variable, and mu is a parameter. We first approximate the solution as a linear combination of reduced spaces phi, whose dimension is a lot smaller than the full order model dimension big N sub S. Then you plug this solution representation into the governing equations. You will end up with an overdetermined system where you have more equations than the unknowns. So to close the system, you apply some kind of projections. Here I have applied a Galerkin projection that gives a reduced system of ordinary differential equations. And by the way, this ordinary differential equation describes the latent space dynamics, which was completely derived from the original governing equation that describes the underlying physics. So this is physics constrained or physics informed latent space dynamics discovery approach. Then you can apply your favorite time integrator to this reduced system. For example, this backward Euler time integrator has been applied here just for the demonstration purpose. This gives us the fully discretized reduced nonlinear system of equations you have to solve in every time step. However, you have to be careful with these terms in red fonts, which is particularly the nonlinear terms. Unfortunately, that nonlinear terms changing every time the argument changes, and it scales with the full order model. So this full order model, embedded full order model, hidden full order model, the dependency is going to kill the efficiency of the reduced model. To address that, the hyperreduction has to be applied. The most famous hyperreduction technique is DEIM, which stands for discrete empirical interpolation method. The DEIM introduces the nonlinear physics phi sub f and expresses the nonlinear terms as a linear combination of the nonlinear the basis vectors. Then it introduces a sampling matrix Z, which selects an important subset of the nonlinear terms. So after the action of Z on the nonlinear term F, only the subset of F will be evaluated. Now the sampling indices of the matrix Z can be obtained through the various algorithms. The DEIM and QDIM are the popular ones. Then the generalized coordinate for nonlinear term f of hat can be obtained by solving the interpolation problem. Then you plug this expression into the reduced system of coordinates for nonlinear term f of hat. And then you plug this expression into the reduced system of equations wherever the nonlinear term shows up. Then you will end up with these crazy looking equations. But if you look at them close enough, most of the terms can be pre-computed. And these nonlinear terms can be efficiently computed thanks to the sampling matrix Z in front of the nonlinear term F. This is how we achieve the efficiency through the reduced order model and hyperreductions. There are many variants of the DEIM, for example, GNET and STGNET and SNS. But the main machinery of the hyperreduction follows this paradigm that I have just introduced here. This traditional linear subspace reduced model can be used to accurately accelerate various physical simulations, achieving a speed up of 10 to 1000 with a relative error less than 1% or the 5%, for example. Here, another variant of the hyperreduction is shown here, the so-called SNS. The usual drawback of the DIM method is that as you increase the sampling points, it's supposed to increase the the accuracy. However, it doesn't show usually those behavior. Sometimes it shows the instability. But SNS method recently we have developed introduces the new criteria. For example, imposing the orthogonality, and that will improve the instability, the issue arising in DIM method. So if you're interested, please check it out. But as I mentioned before, the linear subspace reduced model has been applied successfully to many different applications. For example, I am showing the examples of many different hydrodynamics simulations where the great speedups of 14.6 to 87.8 were achieved. And at the same time, the accuracy was less than 1%, or sometimes even less than 0.1%. And this, the reduced projection-based reduced model, the great advantage of it is its speed up will increase as we apply it to the larger scale problem. Just to see that effect, we have refined the Rayleigh-Taylor instability problems and observed the speed up. Indeed, as you can see from the graph, higher speed up is achieved as the size of the problem increases. Another great thing about the reduced model is its robustness with the extrapolations. Unlike the black box approach, since the reduced model directly incorporates the governing equations for the underlying physics, even though it is used to predict the solution for the parameter point away from the training data, it can still give a reasonable accuracy. For example, this graph shows the relative errors of the local reduced model that is trained at the local points, which is 0.25 here for the pseudoblast simulations. As the prediction points gets away from that point, the accuracy is deteriorates, but not that much. Even though we far away, we get away from up to 0.5 or close to 0, we still get the relative error close to or even less than 1% or close to 1%, which is pretty good. And this has a great implications. For example, in gradient-based optimization, let's say you do not have sensitivity implementation, which is particularly very quite complicated for the implementations. In this case, you can approximate the gradient using the finite difference. Here, for example, you do each function evaluation at some perturbation points using the extrapolation capability of the local reduced model. You can approximate the gradient via the finite difference very quickly. Another implication is that you can easily add more local reduced models to cover the broader parameter domain. There are many variations of projection-based reduced models as well. For example, the solution does not always have to be represented by linear combination of reduced spaces. It can be completely nonlinear, as it is depicted in this slide. The decoder of the neural network of the autoencoder can be used as a solution representation, which is denoted as a G, the nonlinear map G here. When you do that, you are actually increasing the nonlinearity over the original nonlinear, the problems. So the hyperreduction becomes even more important. And when you apply the hyperreductions, the structure of the neural network matters for the efficiency of the nonlinear manifold reduced model. Let's first look at the neural network with two hidden layers as a decoder. Let's say that the orange disk in the output nodes are the selected ones, denoted as this orange node here. And you will notice that many hidden nodes are connected, and as you go deeper and deeper in the hidden layers, the number of connected the hidden nodes are increasing very fast. This actually degenerates the efficiency of the nonlinear manifold reduced models, because in nonlinear manifold reduced model, you need to compute the Jacobian of this neural network using the backpropagations. More hidden the nodes are connected to these selected nodes. The computation of the Jacobian will be a bottleneck of overall the computation. On the other hand, if you use the shallow neural network that is one hidden layer, then you can easily see that the less number of hidden nodes are connected to the sampled outputs, which brings us an ultimate efficiency in the nonlinear manifold reduced model after we extract the subset of such chosen nodes. Furthermore, if you sparsify the structure, then you will get even better efficiency. If you do that, then you will get a superior performance to the linear subspace reduced linear subspace approach. For example, here we compare the performance of different types of the surrogate models that I have introduced in this presentation. The full order model is the full order model and nonlinear manifold reduced model and linear subspace reduced model, and the deep fluids, which is a black box approach. As you can see from the movies, NNROM and the full order model are almost identical in eyeball norm. These two movies are almost identical in eyeball norm, and quantitatively the NNROM achieves a less than 1% maximum relative error. Furthermore, a speed above 11 is achieved by the NNROM, while the LSROM and deep fluids are struggling to achieve a precise solutions. Another interesting variant of the projection-based reduced model is a space-time reduced model, where not only the spatial the domain complexity is reduced, but also the temporal domain complexity is reduced as well. Using the space-time reduced model, we were able to, this movie is always giving, okay, it works now. Using this space-time reduced models, we were able to reduce the 10 billion degrees of freedom to only 10, and still gets the pretty much the same physics response as shown in the movie. The full order model took 17.4 seconds with 256 cores, which is not bad, but the space-time reduced model was able to finish the simulation within 0.006 seconds with only one core. That gives us a wall time speed up of around 2,700. Quantitatively, the relative error is less than 1% throughout the time history. Physics constrained projection-based reduced model have also been successfully applied to accelerate the design optimization process. For example, here is a numerical demonstration for lattice structure design using the component-wise reduced model. Here we minimize compliance, imposing a constraint of mass being at most 40%. The downward pressure force is applied on the top middle ports. Dirichlet boundary conditions are imposed at the bottom corners here. The full order, the monolithic finite element solve involves 2.7 million degrees of freedom for this particular problem, while the component-wise ROM has only about 4,000 degrees of freedom. The movie shows the optimization history from the beginning. Initially, it started with a uniform density variable and evolves into an optimal design, where the blue component implies no material there, while the red component implies that you put the material there. With the component-wise reduced model, a speed up of 660 was achieved, and the tunable accuracy from a relative error less than 1% down to 1 times 10 to the negative 8 was achieved, which was another great advantage of this type of projection-based reduced model. The component-wise reduced model structure, this approach has been applied to stress constraint problem, where the mass is minimized with a stress constraint. This is considered a harder problem than the previous examples. Here we achieve a again, a speed of 150 with a component-wise reduced model with less than 5% relative error in stress measure. This is quite an achievement, by the way, because it is usually hard to obtain an accurate stress measure with surrogate models for lattice structures, such as homogenization-based method or beam or truss-like structures. As you can see from this zoomed picture here, the component-wise reduced model is able to bring high fidelity accuracy for stress quantity everywhere in the computational domain. The projection-based reduced model can be also used as a preconditioner for the linear system of equations. So that occurs during the design optimization problems. Here we have applied the reduced model preconditioner for the wind turbine blade design problem, and Rome was able to achieve a speed up of 3.5 and converges to the same optimal 3D blade optimal design. Another type of projection-based reduced model, that is data-driven local reduced model, can accelerate this time multi-start airplane wing optimization process. Multi-start strategy is commonly used to solve robust optimization problem. It needs to solve many optimization problems with different starting points. In this setting, once for all trained local reduced models were reused to ultimately achieve a speed up of 32.4 times. All right, so much for physics constraint projection-based reduced model. Let me conclude the talk with some summary. The data-driven methods for physical simulations can be categorized by its level of intrusiveness. For example, the black box approach, denoted as BB, is the least intrusive method requiring only data. Then we introduced a more interpretable method, which also use only data, but that try to come up with a model that is more understandable and or the interpretable than the neural network type black box approaches. And then the most intrusive the methods, that is physics constrained methods, can be the last category. Roughly speaking, more intrusiveness means more accuracy. So the intrusive, the physics constrained reduced models are more accurate than the black box approach if the same amount of data are used. On the other hand, more intrusiveness means less speed up. So the black box method is faster than the intrusive reduced models in general. Also, the physics constrained reduced models are more robust in extrapolation than the black box reduced models, which become very handy when solving a PD constraint optimization, such as design optimization. If you are interested in generating the numerical results that I have shown today, you can use our open source software tools for data-driven physical simulations that is called the Libram, which you can find it from this GitHub page here. Also, useful documents and examples are given in the Libram webpage, that is libram.net. So please take advantage of it. With that, let me conclude my talk. Thank you for your attention, and any questions are welcome.
Thanks, Youngsoo. Very interesting.
Thank you.
There was one question in the chat, a general question regarding how a training dataset is prepared for transient simulations. When training a model that has two spatial dimensions and one temporal dimension, do you have to keep the same 2D shape and the same simulation time in the training dataset?
Well, 2D shape, I mean, you mean the 2D versus 3D or 2D versus 1D, right? And yeah, I mean, we use the underlying data from the same spatial dimension, so we have to keep that. But if we have a multi-dimensional fields, not particularly from the spatial dimensions, but also you know, for fluid dynamics, there are different fields like the pressure and the velocity. Even velocity has 3 different components, or the density. So it can introduce many different multiple the fields, and that introduces the dimensionality increase, right? From not just the 3D or 2D spatial degrees of freedom to like much more higher the dimensionality. There, you can take advantage of the multi array decompositions, such as the tensor decompositions, to achieve a greater the compression. Greater compression means smaller the system of equations you will deal with, and that means it will give you the faster speed up and all the good things happens. Yeah, so there are some techniques we can apply and take advantage of. Yeah.
Uduak, yeah, someone's raising their hands.
Hello, can you hear me?
Yeah.
Okay, sorry, this might be a silly question, but when you go to the reduced order models for you reduce in temporal space, I understand that you're increasing computational efficiency and maybe faster simulation, just reducing all of that. Anyway, so my question is, like, if for an instance, let's say you want to predict chaotic event, you want to know when maybe something, how an event happened. Can you apply scaling to the reduced order model to get the physical time? Can you reconstruct to get the physical time where an event happens?
Well, yeah, if you think about it, once you have done a compression, like, okay, so we deal with the full order model, and full order model a lot of times generates the high dimensional data. And in reduced order model or surrogate modeling, a lot of approach, apply the compression techniques, the reducing the high dimensional data to reduce the space. Once you have done that, the high dimensional data information is not gone. It's embedded in the either the nonlinear, the manifold representation, or the linear subspace representations. And once you have reduced that high dimensional data to reduce the space, all we are doing is, as you said, it's a scaling, or the finding the coefficients, appropriate scaling for individual, the basis representations of the high dimensional space, the solutions. And there are, as I introduced in this talk, there are many different ways of the scaling or the finding out those coefficients of the reduced representations. You can use some interpretable, the ODE models, or you can even drive another PDE from the existing governing equations. That becomes the physics constrained approach. Or you could just get rid of all those ODE or PDE businesses, just fit those data into the neural net, the models to find out the appropriate scaling order. So it's that's a actually great way of summarizing this methodologies I have introduced, like what is the appropriate scaling approach you can do. So your question is not silly and very relevant, and so thank you for the question.
And I also imagine that, the purpose of the reduced order model is to have simulations on this model and predict something. Do you imagine that this let's say the percentage error in let's say a time event, do you think that they can grow to, let's say, an order of magnitude? How do you say, how does the error impact? Can you is the exponential, or does it make sense? My question, whatever.
I do understand. So it's predictability you're asking, and in order to assure a certain accuracy is guaranteed when we predict the new simulations using the trained and reduced order model or the surrogate model, and the sampling is really important. So in this slide, I try to illustrate that the uniform sampling, it gives you this is the maximum error is bounded by around 5% or 6% here. But if you use smarter sampling methods, then you can even lower that upper bounds, the error bounds, by factor of 2. So there's a procedure when you apply the sampling method to make sure that wherever you try the predictions in your parameter space, it is guaranteed to achieve a certain level of the accuracy, right? So that the kind of things can be assured and certified while you are building a reduced model. Yeah.
Okay, thank you.
Yeah, I mean, if you want to, I mean, I cannot go into, a lot of details, but if you want to know more about it, you're free to contact me, and then we can have a, we can have a detailed discussion about that if you're curious about that.
Thank you.
Great. I do not have any questions to you, Youngsoo. Maybe anyone else from the audience. Otherwise, we can wrap it up. We have 8 minutes left, guys. Don't be shy. Youngsoo is here now. Make sure you use that time with him. Maybe I'll come up with a question in the meantime when people think, what about how much data are we talking about? So if someone thinks about applying this in the industry, how much data are we talking about so that this really has an impact on my studies, whatever I'm investigating?
Yeah, how much data how much the training data is required. It depends on the applications and also the characteristics of the simulations. Like for example, and also the number of parameters a lot of factors is affecting the how many data you need. So for example, if you have only one control parameters you would like to explore, then relatively small number of data you need to generate. However, if you are dealing with distributed parameters, like every spatial degrees of freedom you want to have a control on, the different parameter you want to apply the different parameter. Then you're talking about like millions or billions of the parameters, and imagine that sampling those the parameter space. It's as you increase the dimensionality, there's the curse of dimensionality applied there when you do the sampling. So enormous of the data is required. So a lot of research is going into that direction for the high dimensional parameter space, how we can efficiently sample the data so that we minimize the number of data. And also not only the parameters, if the solution behavior is advection dominated, which is a certain characteristics of hyperbolic problems, like a lot of fluid, CFD, computational fluid dynamics problems, then there, even though you have a small number of parameters, it tends to requires more and more data there, because there are no intrinsic reduced solution representation exist to cover all those variations of dynamics because of that characteristic of the solution. So, but if the solution is very diffusive and even one, the dimension of the reduced space can capture that very accurately. So depending on the solution characteristics, yeah. So my answer to your question is it depends.
As always, yeah. But thanks for the answer. I was wondering about interpretability and explainability. How do you distinguish those two, and how important is explainability in the case of physics-informed simulations or data-driven methods?
Yeah, it's the black box approach, such as neural network. I mean, we are doing a lot of research right now and try to understand, the behavior of the neural network for the structures. I'm sure at some point we will understand a lot more better on the behavior of the neural net in the future. But right now, it's still black box. And once you have the design some neural network structure, it is what it is. And if it happens to work well, then you are lucky. If it does not happen to well, then you are not lucky. And when it does not work well, it's hard to analyze why it does not work. But on the other hand, the interpretable method and the explainable method, which I was, advocating in this presentation, for example, some familiar the model like the ordinary differential equations or partial differential equation. If you model your surrogate models using ODE or PDE, for example, then it has been studied for hundreds and hundreds years now, and we know a lot more about those ODE and PDEs than the neural network, fortunately. So one of the examples I gave in this presentation was, so for example, if let's say you use this linear ODE, then if you happen to know the eigenvalues and eigenvectors of this explicit reduced operator A sub hat, then you can do a lot of things. And sometimes this model probably is not good. And even though it fails, we know why it fails. And for example, the eigenvalue greater than 1, it gives you the explosive, like the unstable behavior. So, and we know where to look at, and how it also gives you the hint of how to fix it, right? Okay, so we gotta the bound that eigenvalue below 1 for some the trick, right? So that's what I mean by interpretability or the explainability. And we can analyze better, and if it fails, then we know where to look at and how to fix it systematically, not trial and error fashions, which is a lot of times it's done in neural net training, like so-called hyperparameter tuning, right? So you try this hyperparameter, you try this hyperparameter, and it works well, then all right, my life, finally solves. I can go take a break, right?
Yeah. Last question maybe from my end, Youngsoo, is how much do you work with experimentalists to make sure that you're not deriving everything from a simulation, which is also a model, but maybe also validate your results with the real world?
Yeah. So it's a both way. I mean, so the computational model is always checking with the experimental list, and then we improve upon that. And also the experimental lists, they rely on us because we give relying on us, because without our help, they had to do a lot of expensive experiments. But we do ahead of time some computational study, model study, and give them, okay, this is a set of parameters you can focus on your experiments. And that will reduce the number of experiments they have to do, and that also saves the money and time, etc. So we work both ways, and I tend to work with many experimentalists, as I have shown you in this presentations. Mm-hmm. I work with the 3D printing process guys, and also I work with the the experimental guys, like a lot of the physicists are at Lawrence Livermore National Lab, and there are many experimentalists, and
Great. Cool. All right, we'll wrap it up, Youngsoo. Thank you so much for your talk. Would it be possible for you to send me the slides so I can distribute them among the attendees?
Definitely. Yeah.
Awesome.
Will do.
Thank you so much. Great talk, and hope to see you in December.